All right, let me show you an example of metaprogramming in K1. So today what we're going to try to do is implement something that's often a language feature, and it's called bitfields. C has bitfields as a feature. Pascal has something called sets that I think kind of works the same way. But the idea is essentially just to go below the level of 1 byte as the smallest unit of size, or go larger but arbitrarily say like 10 bits. And to talk about, a sort of field or an array of bits, an array of data bit by bit, ascribing maybe a specific meaning to the first 2 bits and to the second 3 bits. And this is really common for like parsing network protocols, network buffers, or persistence formats, just generally something that becomes relatively common in like some lower level programming, and it's often a language feature. And I think that we can implement it just with a bit of metaprogramming in K1. So let's give it a go today. So what we're going to do is we're just going to call it BF for bitfield K1, and this opens up K1 file. We'll go ahead and define main, and let's make it big. All right, for the people, wow, so big. And for now, we'll just print hello bitfield, and we'll return 0. And let's run that. So this is going to be C. I think I have a nice crash. So neovim didn't replace the path like it usually does, but that's okay. So we just ran, and we have hello bitfield. So I've already written the metaprogram, and today I thought we could just walk through it and make use of it. So let's first define the bitfield that we want to talk about. So I think that I would like to have, let's say, I'm just going to use the example that I did before. If that's all right, we'll go to our README, and we're going to go to define, and yeah. So we'll do the starship example. All right. So this is the bitfield that we'd like to define, taking up a total of 16 bits. Ultimately, the code that we'd like to generate would be something like, starship. We'll call it ship flags. And, if we wanted to do a wrapper struct, we would say, we would like wrap a U16, right? And then we could make a namespace for ship flags, and we could start to like write functions, say, make. And maybe it would take a value for each field. So shielded, and then since it's 1 bit, for 1 bit, so we kind of want to represent that as a bool, right? We don't have like an I1 type. I will mention that one way to solve this problem is just to allow arbitrary width integers in your language, which is what Zig does, which is pretty neat. We don't do that here. And so, yeah, that would be a bool. Shielded, and then cloaked, be a bool. Damage could be a bool. And then we have sector ID. And then this is interesting because this is not quite a byte, right? It's bits 4 through 8. I guess the bool already wasn't. And what we would want to do here actually is, let me make sure the gain isn't too high on the mic so that we're not clipping. Yeah, let's lower that just a little bit. Sorry. All right. And so what we would do is we would just go ahead and use the smallest thing that fits. So a U8 here, and then this is relevant because we're going to see a program that does this in a minute. And then we have the foo, because what example is complete without something called foo? And then that would also be a U8. Hopefully you understand where we're going with that. And we would return a ship flags here. And then the other thing we would want to write is some helpers, like is shielded, right? Things that would extract a particular field, get sector ID. Okay, so our goal is to be able to say something like this, meta standard bitfield define u16, and we want to call it ship flags, and give it some fields that we want. So we want a shielded. So let's say that we had a struct here, and we could just pass imagine this is JavaScript, right? Bits1 name shielded, and that would be our first field. Okay, and we kind of might want to format this a little bit more nicely because we're going to repeat some fields. And I hope this is making sense. Let's make a bit more space. And then we have cloaked and damaged. Bits 4 through 8. That's 5 bits. And that would be sector ID. And then we'll go ahead and do 8 bits. And then that can be our foo. And we could write something like that. And then we could try to use it. Like let my ship flags slash, let's just say new or something. Okay. And the hope would be that by invoking this meta program, and the way this meta directive works is that it promises to run the expression that you pass to it, so the first expression that we see, at compile time. And when it's done, it expects a string, actually. And one day it might expect a data structure representing code. But for now, it expects a string of the source code that you would like to compile as if it were right there. And it's a regular function otherwise. So this is perfectly valid K1 code. This is just a list, literal, with a series of anonymous struct literals inside. So all of this is just completely normal code. And now let's look at how we might define the actual bitfield function. So this is in the standard K1 lib standard bitfield. And here's some documentation of the usage, which uses a helper we haven't written yet. And we'll see here one helper function, just a very normal function, and a couple of little constructors where you would just be able to write bn, b1, or b8 instead of the full literal, which makes things a little bit more compact. May or may not be that good. One thing is we have named arguments, so we can say bits equals 8. It does make us name the first one as well, though, so we could go ahead and do that. And then this is our main define function. And as I promised, you know, the signature should be familiar. It wants that base type, and then it wants the name as a string. Now this is interesting because we're passing one thing as a type and one thing as a string, but it's all compile time. So while this is a string, it's really a string constant, a compile time known string for sure. And then the members, which is a view, and view is our list, our read-only slice type in this language, which the fact that I explain it that way means maybe I should call it slice, but I don't like the name slice. I'm not terribly in love with view either, but this is what we have right now. And this is so a read-only array or contiguous buffer of this struct, name string bits. Size is an I64, and so that you end up working with unsigned values a lot less often. And because 63 bits is plenty for most sizes, and then string is a view of bytes, essentially, a length and a buffer. Your normal, same as like a C++ string view. Anyway, and those are all defined sort of, none of these are first class K1 features. These are all written in the core library, if that makes sense. And then we return a string. And let's just walk quickly through the implementation of this function. So first, we're going to bring a type into scope, a string builder, and then we're going to bring an ability into scope. This code writer ability, code writer, is a type class that it's actually implemented for all writers. So if you can write stuff, if you are a writer, then you can be a code writer too. And all you have to do is implement this function line and this function var. Line is a little bit silly, as you can see, but var does some heavy lifting here with the magical way that we can transfer some values from compile time to runtime. It builds a constant. Any value that we have available to us at compile time, we can turn into a runtime constant using var, more specifically using meta/baked variable. And you can't see that. So let me just go ahead and click on it so that you can see what I was talking about here, right? So if you supply, because these are the only two functions of CodeWriter that don't have a default implementation here in this ability, you can see line doesn't have an implementation and var doesn't, but the rest of these functions do. So the only thing that we have to provide when we implement CodeWriter is line and var. If we did not, I don't know if the LSP is going to work here because of which folder I opened the project from. Yeah, and if I save, you can see that we're missing an implementation for function line in ability CodeWriter. So if I now, and then if I save again, we're back. And I wanted to just quickly highlight the responsiveness of this. So, we're seeing instant feedback, and what I have the LSP doing right now is re-parsing and fully compiling the entire core standard and the project every time you save. And we're still, in around somewhere between 0 and 5 milliseconds, and that's including all file I/O, just to type check, not to link and not to do LLVM. But the hope is that all of your dev flow, all of your, you kind of live and breathe in compile time execution and type checking. And so that's the time you care about. You don't really have to wait for the LLVM build as often as you have to wait for just a type check and run a little bit of code at compile time. So back to the main event. We're going to go ahead and grab the base type that we were passed here, and we need to make sure that this is an integer because there's a number of different types available, of types available in K1, and it's defined here in K1 as this type schema either, which is a sum type. So here in my types namespace is where we define sort of the menu of what's possible for metaprogramming currently. And these three functions are the ones that the compiler implements specially, right? The ones that you could never implement yourself. And that's to get at the ID of a type. And then using an ID, we can get a type schema, which is the type we'll look at in a minute, and as well as its name. And all the heavy lifting is kind of done by this type schema either. You can see it remains pretty simple to this day so far. We kind of start with our basic scalars and smaller types and build up in complexity to references, then arrays. Arrays are fixed size, compile time known arrays, like an array in C. Structs eithers, which it's the very thing that we're defining now. It's a series of variants where each variant can have a single type as its payload. And the reason it can only have a single type for its payload is because it's very easy to just make the payload be a struct. And now you have a type that is the payload, unlike in Rust, where you're able to provide sort of an inline payload, and then you have no way to talk about the type of that payload. So because we only accept one, but we allow anonymous types, you have this very convenient. This is very terse. We didn't have to define names for these types separately. There's a lot going on here, but we have, this is a struct, right? And it's a series of fields, which each have a name, a type ID, and a byte offset. Here's an optional payload for each either variant as well, with the prefix ? And option is just another type defined in the language itself, not a built-in. Although the syntax for that ? Prefix is a built-in. So we're going to retrieve one of those schemas for, so we see base schema is a type schema. And now we're going to pattern match on it using this require statement, which is a lot like Rust's let else. So we're going to say, here's the pattern match, it's this part. So it's expression is, and then pattern. And then we're going to match on the variant int of type schema. And then we're going to bind to int kind. This is also a pattern, but it's a variable binding pattern. Otherwise, we're going to crash. And if we crash at compile time, this just generates a compilation error, which is exactly what we want. And now we can use int kind on the next line. And so now we know how many bits we're working with. We're going to declare a string builder. We're going to call it code because it's also going to work as a code builder because we have this ability in scope that sort of teaches it new things. And then we're going to write the code that we would want to write otherwise. So first we're going to do a def type of our type name. This is exactly what we wrote by hand over here in the other tab. Def type, ship flags, right? We're going to declare a bit of state for the loop, whereas we're going to loop through each of these bit fields, and we do it as a pointer so that the lambdas can capture it here. But here's sort of the main heavy lifting of this, and the point of this is not the logic of constructing a bit field, but just the fact that it is normal logic. So we're going to make a little member info list that we use to generate the rest of our code. So we're going to do one pass to do like the heavy lifting of calculating the layout and layouting the bit field, and then we're just going to consult our member info as we like splat out the actual source code. So it's kind of not super important what all of these things are. We're going to construct it list.fromMap, which is a terrible name. It's like get me a list by mapping over members, which is a list. So anything that can be iterated over, we'll get a list from it. Really what it is I had built-in syntax for doing this, and I replaced it with a function very hastily, and my goal was to get the built-in syntax out of the language, and I didn't really spend too much time thinking about what this function should be called. But it's we're passing a lambda here for each member, right? So list like from mapping, right, is kind of a better way to think about it. There's no map here. We're just making a list by mapping. And then, for each member that's passed in, so in our case, it's going to be 5 members. Let's just print. Println. I think that we just have name. We'll do name capitalized. Member.name, because we capitalize the name for some cases. Name cap. Okay. And just to show, let's see. Yeah. So now, because I updated the code in the core library and then I saved, we see an info diagnostic coming out here and this is caused by the print line. So this is the print that we just wrote. Shielded, cloaked. So you can see it's capitalized. So hello from the other side, the hello from the other slide. And if we save, that's just the print line that we just wrote. So it's really nice because you can really use this to interactively program just using a basic LSP enabled IDE or editor. Like here I'm using NeoVim, but it's all sort of done in terms of the LSP workflow, which is pretty cool. I did some syntax for this. So shift left can now be written that way. It's still ability bitwise. So you can implement that operator for any type by implementing the bitwise ability. It just so happens that we implement it intrinsically, like as a built-in for the integer types. So impl bitwise, you can see for all of our base integer types, we do an intern, so like an intrinsic built into the compiler implementation. This lets you do operator overloading if you want, but also it makes the syntax a little bit less special and accessible too. I did bit and as well, so I don't have not though yet. I don't have the like a prefix unary up there. Okay, I might not even need this. I think. Okay, yeah. Cannot cast reference to U32, so we do. All right. So and then we just form a struct here anonymously. Notice I never had to define the struct, but it is a fully statically known fixed layout struct as if I had defined it separately. We're just inferring its shape from the types of each of these variables. If I want to check member info, the hover is actually going to show me the type. So it's a list, and this is misparsing as markdown the message that isn't markdown, which is why everything is a little bit angry. But we can see that it's a list of these structs, and the compiler just figured out the struct type from when we constructed it. Okay, so now we're going to make a mask for each member, because that might be useful. We're going to declare a 0 value to initialize these flags with 0. We're going to go through each member, and if it's a bool, If bits is 1, then we're going to model it as a bool, special case. Otherwise, we're going to do the bit width. So, and type width came from our function. So this is never going to be like U5. This is going to be either U8, 16, 32, or 64. Let me just do a comment here. Hello, friends. We'll just throw that in. And then I want to show, let's see. So you can just see this is regular code, appending to a string builder, if statements, a normal loop. This for loop, because members implements iterator or iterable, that's how this desugars to. It makes an iterator and it calls next on it in a normal while loop. So some sugar there, also based on the type class system. And then we're generating a print function as well for our bitfield so that we can pretty print it. We'll take a look at how that looks in a second. For now, let's look at our generated code. So what I should be able to do is go into our outdir. And yeah, let's do the most recent one. I think maybe there's 2 meta programs running. So when we expand a meta block, we actually put the generated code in a file so that a debugger could find it and so that you can just look at it. So this is the code that we're actually generating. And to prove it, let's go find our little hello comment. Hello friends. I don't know, let's put hello friends after the namespace declaration, maybe. NS type name, hello friends. All right, and we'll save that, and let's make sure that we've saved since adding that code. And now we'll go in here, and hopefully we have one from this minute. Yeah, we do. So NS ship flags, hello friends. So this is our generated code. I don't know if the LSP works in here. Yeah, might be. Oh yeah, this file has changed since Freddy. You know what to write it? No, let me just load it. All right, that's fine. Can I do this? Yeah, okay. So we'll just refresh. And this is the code we've generated. So we did a getter and a setter for everything. I wonder if for the getters, if it's a bool, we should do is shielded. So like is cloaked, right? And then if it's not a bool, if it's bigger, so like the sector ID, which is 5 bits, we would do get. And here's our print implementation. So we're going to implement print for ship flags, which means we have to supply print to. And this is what we do. We print each field. Really simple stuff, but that you might not want to write yourself every time you have a bit flag, bit field. And let me just consult my README here to grab like an example of setting everything to save us a bit of time. Okay, and then we called it ship flags. So we'll go back to ship flags and we'll write it this way. So, whoops, forgive me. Okay, so these are just methods. I think I have to do it. Okay, my parser is not very smart, so we're gonna leave everything on the same line for now. And let's print X. So let's just print line our flags are, and then we'll do that. And because we implement print to, what this interpolated expression is going to expand to is a string constant here, compile time constant. We're going to push that to a buffer. We're going to call print2 on X, and we're going to push that to the buffer. And then we're going to have an empty string constant at the end as well. I'll push that to the buffer. So I think it might even desugar if I hover it. But anyway, so that's why that's working. If we didn't implement print, then this wouldn't work. And I guess we can, let's do all of this at compile time so that we can see what we're printing. So we'll just say static, and then we'll do a block of code. And then that's going to run now at compile time. And type ship flags exists. Right, so I don't know. I think the error is appearing in the meta program, sadly, not here. So that's interesting. And there, let's save. And we see function not found new. That's right. It's actually just 0. We don't even need let my ship. So here's our X. And then so now we get our blue because we printed something. And we see that our flags are shielded true, damage. Shielded, cloaked, damage, shielded, cloaked, damage. That is the order that we passed them. Okay. And we're never setting cloaked. And cloaked is false. So that's good. Let's set shielded to false. And then we can see that shielded is false. The sector ID is 17. If the sector ID were 18, we're going to see that the sector is 18. And then let's also do this at runtime. So we're just going to do like, we're just going to call it test. And then we're going to do exercise our code in here. And we'll call test statically so that we can still see it. But then we're going to call it at runtime as well. Okay. And then what if we wanted test to return our ship flags? So let's have it return our ship flags as well. And that way we're going to see it as a constant in the final LLVM output. So yep, just checking that the recording is going. All right, and let me run this. So run this time, or what was my command? Yep, run the current directory to the compiler, and we see that our flags are, and this is a completely different execution engine. This is going through the LLVM backend and then running a native binary .k1 out / example, right? That's what we're running. It's just a native executable here, but we see it's printing the same thing that we're printing at compile time, using our VM to interpret to execute our bytecode instead. And yeah, one last thing, maybe we want to just look at the LLVM output. So if we were just going to do k1 build write LLVM build dot. Now I would hope that we have an example.ll. So we have the, and this is the LLVM bytecode. Here's the LLVM text IR. And I guess the main thing that I want to show, we have hello bitfield here. We want this ship flags. So our flags are, it's going to be let global flags ship flags equals test. And you can, on the right-hand side of a global, you can do anything that's runnable statically. So you can just call a function here. It's going to run at compile time. That's going to do our print. And then I wonder if now, if I were to do this with write LLVM, there they are. So here's our ship flags. We just end up with -3956 in decimal as our flags. All right, so I think that's all I wanted to show. I hope you enjoyed the video. I find this to be really fun way to program. I think the combination of the language, letting you just define types inline, but be very specific about what you want, together with being able to just run code at compile time and also to emit code at compile time, just makes for like a really fun, productive sort of setup, especially with the LSP integration, where you know, I could see myself doing sort of like codecs, SQL bindings, like for ORM, you know, all that stuff, you know, using this. I think it's all there already, and quite a lot of fun and working really well. And I think showcases a lot of design coming together in a healthy way after a lot of work. So appreciate the watch, and stay tuned for more useful, cool stuff hopefully to come out of the project.